Okay, I think it's time to start. So let's start this session of FOCS. This looks like it's the quantum session. The first talk is going to be by Simon Oppers. It's on quantum speedup for graph sparsification, cut approximation, and Laplacian solving. Okay.
Perfect. Thanks for the introduction. Yeah, so this is a joint work with Ronald de Wolf, who's at QSoft CWI and University of Amsterdam in the Netherlands. So what we did is we studied quantum algorithms for really graph sparsification, and then cut approximation and Laplacian solving are kind of applications of this. So let me start by talking about graph sparsification. So what do I mean by graph sparsification? We'll be considering undirected weighted graphs with n nodes and m edges. And in graph sparsification, what do we mean by graph sparsification? We mean that we're given some input graph G, which might be dense. So this can have up to something like n squared edges. And what we want to do is we want to reduce the number of edges while preserving interesting quantities of the graph. So a very sort of trivial and well-known example is a spanning tree, which is a very sparse subgraph, which kind of preserves the connected components of the input graph. But what we want to do is we want to preserve somewhat more intricate quantities. In particular, by spectral sparsification, we mean a sparsification process that approximately preserves all the quadratic forms. So these are the quadratic forms in the graph Laplacian, denoted by LG for the graph Laplacian of G. And you can just think about this as sort of linear algebraic representation of the graph. And we basically want to find the sparser H such that the quadratic forms in H approximate those of G. And why would we be interested in these quadratic forms? That's because they include things like cut values, eigenvalues, random walk properties, and so on. And so in particular, since we preserve cut values, we would also preserve things like connected components, and this kind of stresses how sparsification or spectral sparsification is like a more intricate form than, say, constructing a spanning tree or something like that. So this is, of course, a very nice notion, but can you actually sparsify while preserving these things? And through a long line of work, it was shown that actually this is possible. In fact, it was shown that every graph has an epsilon spectral sparsifier with a number which is only O tilde n over epsilon squared. So this tilde in principle is not necessary. You can even do it without the tilde, but if you want to find it efficiently or very efficiently, then you need the tilde. So this is very sparse, right? If epsilon is a constant, you basically get a number of edges which is near linear in the number of nodes. So this can be up to almost a quadratic improvement. And yeah, these can be found in time near linear in the input size m. So this is a building block of many near linear time cut approximation algorithms. And it's an important, in fact, it's a crucial component of the breakthrough work by Spielmann and Teng on near linear time Laplacian solvers. So what we did is we developed a quantum algorithm to construct such a sparsifier. So instead of O tilde m, which was the time classically, we get it down to O tilde square root mn over epsilon. So for dense graphs, this basically brings down the complexity from n squared to n to the 3/2, something like that. And then we showed that this is optimal, right? We showed that there's a matching lower bound up to polylog factors. And finally, we just get a sort of slew of applications for quantum speedups in cut approximation and Laplacian solving and other things. So in this survey, I'll mainly zoom in on this quantum algorithm that we developed. So to do so, I'll start by talking about the classical sparsification algorithm that we took inspiration from, which is by Kutz and Su. So what they did is basically in step 1, they constructed a near constant number of graph spanners. And graph spanners are kind of combinatorial objects, which you can think of as a somewhat more refined notion than spanning trees. So spanners not only preserve the connectivity, but also preserve approximately preserve distances in the graph. And these are kind of well-studied objects, and they show that if you construct these, then you actually get the most important edges in the graph. So what you do is you construct a near linear number of these, near constant number of these, and you keep these edges. And then the remaining edges in the graph, which can still be like the largest share of the edges, we downsample them with probability 1/2. So every individual edge, we keep it with probability 1/2, and if we keep it, we double its weight. This is basically to preserve the expected value of the weights. Right, so you get this picture where you have some input graph an input graph with m edges. You construct a sparse spanner, which would be like the red edges, and then you downsample like the remaining edges with probability 1/2, and you kind of iterate this. If you do this a logarithmic number of times, then you end up with a spectral sparsifier which has approximately n/epsilon² edges. Okay, so this is this Couteau algorithm that we started from. And so what did we do? In our quantum sparsification algorithm, the first thing, and this is kind of the workhorse of the quantum algorithm, is we constructed a quantum algorithm which speeds up the spanner construction, right? So recall that these spanners are sort of these combinatorial subgraphs, and you can use them to identify, in some sense, the important edges of a graph. And so we showed that we can improve the complexity of constructing a spanner from O tilde m to O tilde square root mn. For this, we combine the classical spanner algorithm by Torp and Zwick, but with a quantum shortest path tree algorithm by Duur, Heiligman, Heuer, and Malla. And then there's, of course, some remaining details, but that's kind of the gist. And this is the first step of the Couteau algorithm. And then we want to downsample the remaining edges. But of course, there can still be something like n² remaining edges. And so classically, you just skim through the list and you toss a coin per edge. But quantumly, we can't do that because we want to do things in sublinear time. So you have to kind of implicitly downsample these edges. And for that, we use a thing called a k-independent oracle, which in some sense simulates access to a large random string. So it's not going to be exactly random, it's going to be k-wise independent, but this suffices for a purpose. And we can kind of query this oracle to tell us which edges are still present and which we threw out without explicitly doing that. If we combine these things, we get a quantum sparsification algorithm which has complexity something like square root mn over epsilon squared, which is not quite what I promised. So we need one more step, and this is sort of a bootstrap trick to improve the epsilon dependency down to square root mn over epsilon. So roughly what we do is we first use these first two steps to construct a rough spectral sparsifier for constant epsilon. And then we use this rough spectral sparsifier to basically create a better sparsifier of the original graph. So this rough spectral sparsifier gives us information that suffices to basically construct a better sparsifier. That's why it's a sort of bootstrap trick. So this gives us the sort of main result, which is that we can construct the spectral sparsifier in time O tilde square root mn over epsilon, and this is tied up to polylog vectors. Now what we can do, and this is kind of nice, is we can basically now combine this algorithm with classical algorithms for calculating certain quantities of the original graph, right? Because recall that the sparsifier is a very sparse graph that preserves certain properties of the original graph. So if you want to estimate a property of the original graph, and this property is preserved by the sparsification, you can just estimate it in the sparser graph. But a sparser graph only has O tilde n edges, something like that. And so a classical algorithm can typically solve a lot of problems in O tilde n time. And this is particularly the case for things like min-cut, max-cut, sparsest cut, solving Laplacian systems, and so on. And so basically by cascading these two algorithms, we get O tilde square root mn time quantum algorithms for epsilon approximating these things. Okay. Then maybe I'll round up by just highlighting some of the open questions that are still remaining in our work. One of them is that, so we proved a matching lower bound for sparsification, so matching up to polylog factors. But this was quite involved, and actually it's not quite what we like, because in the end, sparsification is just a tool, and what you actually want to do is solve, say, approximate min-cut or solve a Laplacian system. So it would be much nicer to get lower bounds for the applications rather than the tool, right? And so we tried it for a bit, but it seems not quite that simple. And then a question that I think is maybe even more interesting is that we showed that our sparsification algorithm is tied up to log factors. But this is for weighted graphs, and the lower bound explicitly uses this sort of weights in the graph. And we're actually hopeful that for unweighted graphs, you can get it down to tilde n over epsilon squared, which is optimal, of course, because the sparsifier basically has size tilde n over epsilon squared. Now maybe I'll just briefly mention some follow-up work that'll show up on the archive later this week. This is work that I did with Troy Lee. And we showed that we can also use this quantum sparsification algorithm and do some more work to basically get a quantum algorithm for exact min-cut. This is only for simple graphs, and the number of queries is tilde square root mn. So we can not only use the sparsification to approximate quantities, but we can actually, by being a bit smarter, also get exact quantities of the original graph. Okay, so I'll round up with that. I'll thank you for your attention, and I hope that everybody can stay safe.
Thanks for the talk, Simon. All right, we have time for questions. Please feel free to just unmute yourself and ask a question, or type something in the chat, either way.
I have a quick question. This is Salil. It looks like in the case of sparse graphs, your algorithm, the output size is bigger than the running time of your algorithm. So like n over epsilon versus n over epsilon squared. So is there some compact representation that you have of the sparsified graph in that case when you don't have enough time to write it down?
Okay, so that's a very good question, and I didn't quite mention this, but sparsification only makes sense in a certain regime, right? Because if your input graph only has n edges, then you would never construct a sparsifier of size n over epsilon squared. But basically, if your graph has less than n over epsilon squared,
yeah,
you just output your original graph.
Oh, good. Thanks. Sorry. Yeah, I was confused.
Okay, sure. No, that's fine. Thanks for asking.
Other questions? We have time for another question. Well, maybe I'll ask one if there's no other questions. Why do you think there's a better algorithm for unweighted graphs? Is the same phenomenon also seen classically?
No, so classically you don't have this distinction. And I think that one example, for instance, is that if you want to construct a spanning tree quantumly, so let's say a minimum weight spanning tree in a weighted graph, then the complexity is square root mn. But if you don't care about the weights and you just want to output a spanning tree, you can do it in O tilde n. And you get the same thing for other sort of quantum algorithms. That things really become easier if the graph is unweighted. Like the intuition is that if the graph is weighted, then you can basically have a lot of edges that don't matter because they have like a tiny weight. And so by adding more edges, you can make the problem harder. But for unweighted graphs, this is not the case, because typically if you add more edges, then a lot of problems become easier, like finding a spanning tree, for instance.
Okay. All right. I guess we're close to the next talk. So thanks again for your talk, Simon. And
sure.
Let's have the next presenter on their screen. All right, so our next presenter is Dao Chen.
Hi.
Hey, Dao Chen. All right, do you want to try presenting your screen? Let's see if that works.
Yeah. See it?
Looks good. Your slide's a little smaller on my screen. That could just be me.
Is it smaller for everyone?
I think the orientation is portrait instead of landscape. That's probably why, because it's yeah, that's okay. Let's okay. I think it's 15 minutes after the hour. We can start now. All right, so let's start the next talk. This talk's going to be given by Dao Chen. Wang, and it's on symmetries, graph properties, and quantum speedups.
Okay, so thanks for the introduction, Robin. So today I'm going to be talking about our recent paper, Symmetries, Graph Properties, and Quantum Speedups. I'm Dao Chen. The full version of our paper is at archive 2006.12760. And this is joint work with Shalef Ben David, Andrew Childs, Andras Guillen, William Kretschmer, and Zupata Potter. So our work is concerned with quantum speedups in the query model. So let sigma be a finite alphabet and f be a known Boolean function on domain D, which is a subset of sigma to the n. The question we ask is how many positions of the input x do we need to query to compute f of x with high probability in the worst case? And the answer to this question is denoted R of f and Q of f in the classical and quantum cases respectively. And when we talk about the quantum case, we assume that we can query the input x in superposition. So we want to know when R can be super polynomially separated from Q, and when R must be at most polynomially separated from Q. So in the former case, I'll be talking about large speedups, and in the second latter case, it will be small speedups. So here's some interesting facts. The first one is when the domain is sigma to the n, there can only be small speedups. On the other hand, large speedups do exist. That's why we're really interested in quantum computing. For example, in 1997, Simon exhibited an f with R of f equal to square root of n, but Q of f is equal to the log of n. So our first main result is a characterization of quantum speedups for symmetric functions. And the motto is that it must be small for hypergraph-based symmetries, but otherwise it can be large. So what are symmetric functions? A function is symmetric with respect to a permutation group G acting on its indices, the set 1 to n, if essentially the domain of the function is invariant under G. That's the first condition. And also the function itself has values, takes values that are also invariant with respect to G. That's the second condition. So for example, if G is the full symmetric group Sn and the inputs are just bit strings, and consider the function f that computes whether the input has a certain Hamming weight, that function is symmetric with respect to Sn. Basically because the Hamming weight of an input bit string does not change however much you permute it. So it has been previously known that when G is the full symmetric group Sn, there can only be small quantum speedups. So our result in this paper, our first result, goes much further and can be summarized by the following flowchart. So here, green means there can be a large quantum speedup, and red means there can only be a small quantum speedup. So let's start at the top. You give me any permutation group G. If it has small base size, then it's green. Otherwise, if it has large base size and is primitive, then we find that it must contain adjacency matrix hypergraph symmetries, in which case it is red. If it is imprimitive, on the other hand, and breaks into an unbounded number of primitive groups, it's also green. But if it breaks into a constant number of primitive groups, at least one of which has small base size, then it's green. But if none has small base size, then actually we don't know, but we suspect it should be red. So there are two salient points of this flowchart that I want to just highlight. The first is that it is complete for primitive permutation groups, for which we see that the quantum speedup is entirely characterized by the base size. If the base size is small, then there can be a large quantum speedup. If the base size is big, there can only be a small quantum speedup. The second thing I want to highlight is that in the red part of this flowchart, we actually prove that R is of order Q to the 3p for p-uniform hypergraph symmetries in the adjacency matrix model. And I do want to stress that this result only holds in the adjacency matrix model, because we can actually construct an exponential quantum speedup for graph property testing in the adjacency list model. This construction is based on the so-called glue trees problem, where we're given access to the adjacency list of a glue trees graph and the label of its entrance. So glue trees graph is what is illustrated here. And the problem is to find the label of the exit. So it has been known since 2003 that there exists a quantum algorithm that performs exponentially faster than any classical algorithm. However, this problem is not a property testing problem for 3 different reasons. The first is that the label of entrance is actually given in this problem, and normally you don't have such kind of advice at the beginning. The second is that the label of exit, i.e. the answer, can actually change even if the graph does not. And third, it is not in the form of a property testing problem, where you have to distinguish essentially between yes and no instances that are guaranteed to be constant far away from each other. What we can do, however, is use the glue trees problem to construct a property testing problem with exponential quantum speedup. And the property we want to test is whether an input graph looks something like what's drawn on the left here, or whether it is constant far away from that. So note that each of these candy-shaped graphs, subgraphs, look like a glue trees graph, but with kind of what we call 2 antennas attached to the left and to the right. So the idea of the proof is that we can classically property test the entire glue trees if we mark the 2 leaves, if we mark the leaves of the 2 trees that are glued. But we'll mark the leaves in a way that can only be read efficiently by a quantum computer, but not a classical computer. And to do this, we will use further copies of the glue trees problem. That's why you see kind of the multiple copies of the glue trees problem in this picture. Essentially, what we do is that we will hide the marking of whether a leaf is, whether a vertex is a leaf or not, as the parity of bits stored at the roots of a glue tree, so that any algorithm that can read the marking must traverse the glue trees. And from the previous slide, we know that this is quantumly easy, but classically very hard. So, so we see that quantum speedups of computing graph properties depend significantly on the input model. In the adjacency list model, as we've just seen, an exponential quantum speedup exists even for the restrictive problem of graph property testing, whereas in the adjacency matrix model, there can be at most a polynomial quantum speedup. In fact, R is at most order q to the 6th power. And these 2 results resolve an open problem first posed by Unbinus, Charles, and Liu in 2010. That was also highlighted in a property testing survey by Montanaro and DeWolf in 2013. So I see I have like maybe 1 minute left. So thank you for your attention. And since I have some time left, so here are the open problems from our work. So we showed that R is q to the 3p's power for p uniform hypergraph properties, but we don't know how tight this result is. We don't even know how tight it is for the case p is equal to 1. The best we know is that R is at there exists an F for which R is omega q squared, and that's just, I think, Grover. The second question is, as you've seen, there's a kind of a slight gap in our characterization theorem. And the question, of course, is can we complete that theorem? And the third question is, as you may have also seen, the graph property we're testing is somewhat convoluted, and it would be great if there was a more natural problem that emits a superpolynomial quantum speedup. And so, thanks for your attention.
Thanks. Thank you for the talk, Daochen. All right, we have time for questions. All right, let me get the ball rolling. For your relationship for P uniform hypergraphs, the relationship seems to get weaker as P gets larger. Is this what you would expect, or is this something you think it's just an artifact of the proof technique?
So for this result, it is known that there exists an F for which R of F is equal to omega Q of F to the P's power. So in some sense, it is like this scaling is kind of, at least the linear scaling in P is kind of in the exponent is kind of necessary. But with respect to the 3P, I mean, it's not even known if it's like tight for P is equal to 1. It's kind of, yeah, somehow it's like a reduction to the collision problem, that, which has, that's kind of where the 3 comes from. Like collision has like something to the 1/3 power. And yeah, I feel like that might not be, so this 3 like might not be necessary. But the P is not necessary.
Right, but the P is necessary. So it's, okay, cool. Any other questions?
Yeah,
Nope,
so quick question. So you're saying that the 3 might not be necessary, but it also cannot be 2 or 1.
Well, I mean, so it can't be 1 because the thing was 2. It can be 2, I guess. Yeah, I mean, it can be 2.
Because you were mentioning a collision problem?
Yeah, I'm kind of mentioning the collision problem because that has like a 1/3 in it, and that's roughly like where the 3 comes from. But the reduction itself is not like, it's not necessarily tight. Like, so it's a reduction to the collision problem, but like if it was like somehow like a tight reduction, then like maybe this 3 is necessary, but it's, yeah, it's
Okay,
not
I see.
a tight reduction. It might not be.
Thanks.
All right. Okay. Maybe let's thank Daochen again virtually, and thanks so much. Okay, let's maybe the next speaker, Laura, can get set up, or Dave, who's.
Yeah, it's gonna be me.
It's gonna be Laura. Okay, great. All right, and try sharing your screen. Let's see if that works.
How does it look?
Looks good. Looks good. Okay, let's wait. Yeah, let's wait 1 more minute.
Okay, for me it says sharing is paused, but you still see it?
I see your title slide.
Now
If you want to try going back and forth.
Okay, so now you don't see the next slide.
No.
Okay. All right. All right. Okay. What about now?
No, now I see your source. Like there's a slide on undecidability.
Okay. All right. Let me try something else, maybe. How about now?
I see your slideshow view now. Okay, now I see the title slide. Oh, that looks good. Now I see the graph isomorphism.
Okay, perfect.
Okay. Okay, I think we can get started. We're 30 minutes past the hour. Okay, cool. So let me Okay, so our next talk is going to be on quantum isomorphism is equivalent to the equality of homomorphism counts from planar graphs, and the talk's going to be given by Laura Manchinska.
Okay, so I want to tell you about this connection between three different areas, namely quantum information, counting complexity, and this abstract area of mathematics called quantum groups. And this connection is supplied by this notion of quantum isomorphism. So let's see what it is. Well, first, the usual notion of graph isomorphism. It just encaptures this notion, right, that two graphs are the same, but perhaps we've labeled the vertices differently, so it might not be obvious from the start that it's the case. Right, and really this problem of graph isomorphism is central both in complexity theory, but also in combinatorics and discrete mathematics. Now, more formally, we could define graph isomorphism in terms of existence of a permutation matrix that conjugates the adjacency matrix of one graph to that of the other. Okay, and now, this adjacency matrix is just a 0-1 encoding of your graph, where you put a 1 wherever you have an edge between two vertices. Okay, and this permutation matrix tells you how you should permute your vertices to see this correspondence between the two vertex sets. Okay, but in order to get to quantum isomorphisms, we actually need to take a slightly different perspective via interactive proof systems, or I'm going to call them just non-local games. So here we can think that we have two provers, Alice and Bob, and they're trying to convince a verifier that two graphs, G and H, are isomorphic. How does this proof system work? Well, the verifier is going to take two vertices of G. He's going to send one to Alice and another one to Bob. And then our provers will respond with two vertices of H. So some H and H prime. Okay, and now in order for a verifier to accept, we want that the H vertices are related in the same way as the vertices from the graph G. Now, what does this relation mean? Well, if you take two vertices from a graph, they could be related in one out of three different ways. For example, they could be adjacent, or then they could be the same, or they could be distinct and non-adjacent. All right, and now our provers, they can agree on some strategy they want to use beforehand, but we're not going to allow them to talk to each other after they have received these question vertices G and G prime. Okay, and we will be interested in the question, when is there a strategy for our provers that allows them to win this game with certainty, irrespective of which vertices G and G prime the verifier had selected? All right, now the way that we actually designed this game was so that this problem of isomorphism is captured by it, namely that two graphs are isomorphic if and only if you have a strategy for Alice and Bob to win this game with certainty. And this is not too complicated to see. All right, but now in general, we know that kind of the expressive power of such proof systems can drastically change if we now give these provers entanglement. So we don't change the game, we just change the class of strategies that we allow to our provers. Now, what is a quantum strategy in such a game? Well, Alice and Bob can share some state, and then depending on the question that they receive from the verifier, they can choose some local quantum measurement to perform on this state. Okay, and then without loss of generality, we can assume that they simply respond with the measurement outcome, which is a vertex of H. Okay. So now there are two ways we can model composite quantum systems in quantum information. One is called tensor product model, and the other one is commuting model. Now, the model we work in is the commuting one, but really you can see the difference between the two only if you allow infinite dimensional spaces. Okay, so now we define quantum isomorphism, and I'm going to denote it using this congruent sub QC symbol. If there exists a quantum commuting strategy that allow these players to win the game with certainty. Okay, so this is what quantum isomorphism is. Let me just give you a couple of facts about this quantum isomorphism. Now, despite this kind of operational definition of quantum isomorphism, you can actually obtain what we refer to as matrix-based characterization of a quantum isomorphism that syntactically looks very similar to how we could express graph isomorphism in terms of existence of a permutation matrix. Now, in this case, what we need to find is this object that is known by the name of quantum permutation matrix. And such matrices are studied in this area of non-commutative mathematics, namely quantum groups that I mentioned before. Okay, you could think that this quantum permutation matrix is some sort of a generalization of a permutation matrix where you replace every entry in your permutation matrix with a projection, so with a matrix. All right, so another thing I want to mention is that this problem of testing whether two graphs are quantum isomorphic is actually a complete problem for this zero gap variant of complexity class MIP with commuting provers. Right? And also we know that it is an undecidable problem to test whether two graphs are quantum isomorphic. Okay, so it's not just that it's hard to test, it's really undecidable to test. Now, next thing you might want to wonder, how do these graphs that are not the same but quantum isomorphic, how do they look like? Well, in general, there's no algorithm to test this, but we have a construction that lets you produce pairs of such graphs. Let me just show you two that come out of this construction. They have 24 vertices each, and I actually need 2 slides to show them to you. So this is one graph, and this is the other one. Okay, and this is the smallest example we know of. Okay, they are quantum isomorphic, but not the same. Okay, so now that we've seen a little bit about this quantum isomorphism, we could ask, how about people who don't know anything about quantum information? Is there some way they can think about this quantum isomorphism? Okay. And it turns out that the answer is yes, and it is supplied by this notion of graph homomorphisms. Now, these are just adjacency preserving maps from the vertex set of one graph to that of the other. Here's an example. So you take a 7-cycle and you can map it into a 5-cycle using a graph homomorphism. Now, you might also want to ask, given two graphs, F and G, how many homomorphisms are there from F to G? Okay, now this is a counting problem. You want to count these objects. Let me denote this number by hom of F, G. Now, a very nice and classic result by Lovas says that you can actually determine a graph from these homomorphism counts. Okay, so more precisely, so two graphs are isomorphic if and only if they have the same number of homomorphisms from any graph F. So what this says is that you can think of these homomorphism counts as providing some sort of measure of similarity between your two graphs. So with this in mind, you could ask, what happens if instead of all graphs, I put some kind of other nice class of graphs? And it turns out that many relations on graphs can indeed be characterized by choosing appropriate class of graphs. So for example, co-spectrality is characterized by equality of these homomorphism counts from all cycles. So in this case, this class of graphs is all cycles that we are considering. Now, if you look at fractional isomorphism, which is this linear relaxation of graph isomorphism, then that is determined by equality of homomorphism counts from the class of all trees. And there's also a generalization of this tree result, where you replace all trees with graphs of tree width at most k. Okay, then you get this notion known as k equivalence of the two graphs. Now, what about complexity of testing these things? Okay, so for graph isomorphism, we know we can test that in quasi-polynomial time. Now for co-spectrality, fractional isomorphism, and this further relaxation of k equivalence, we can test that in polynomial time. So that implies that these things on the right-hand side, right, the inequalities of the corresponding homomorphism counts, we can test in with corresponding time complexity, right? So for all graphs in quasi-polynomial time, then for cycles and for trees, or in general graphs of tree with most k, we can test the equality of homomorphism counts in polynomial time. Now, you might ask, what is the class of graphs, nice class of graphs that I still don't have on this slide? Well, it's planar graphs, and actually Delgro and Rattan, they ask, what happens if you look at the class of all planar graphs? What is the resulting relation on graphs, and what is the complexity of testing equality of homomorphism counts from all planar graphs? I bet this is not what they had in mind, but what we show is that the answer is that the relation what you get is exactly quantum isomorphism. Okay, so two graphs are quantum isomorphic if and only if they have the same number of homomorphisms from all planar graphs. And a consequence of this, because bear in mind, I said that testing whether two graphs are quantum isomorphic is an undecidable problem. This implies that the complexity of testing equality of homomorphism counts from all planar graphs, this is an undecidable problem, which is strange, right? Because class of planar graphs is nice, so we would have expected to have a more tractable answer to this complexity question. All right, I'm probably out of time, right, Robin?
Yeah, ideally we should leave some time for questions.
Okay, all right. Then thank you very much. I'm ready for questions.
Well, thanks for the talk, Laura. Okay, questions. Okay, maybe I'll ask a quick question then. This might be difficult to explain the intuition for, but why do planar graphs show up for quantum? Like, where's planar coming from?
Yeah, we would also like to know like an intuitive answer. It kind of comes out of the proof, but I don't have any kind of philosophical insight of what does quantum mechanics have to do with planar graphs. Yeah.
Okay. Oh, there's a question in the chat, maybe. Let's see. It says, the graphs that are isomorphic but not quantum isomorphic look quite dense. Are there examples of planar graphs or less dense graphs with the same property? So the property being that they're isomorphic but not quantum isomorphic.
Yes.
Or maybe quantum isomorphic but not isomorphic?
Yeah, we haven't looked into that, and somehow, like in general, like all we have, the only way we know how to construct such pairs of graphs is via this construction. So it by no means gives us a complete picture of what are these graphs that are quantum isomorphic, but not the same, right? And remember, like we cannot just produce these examples at will because it's an undecidable problem. Yeah. So I don't know the answers.
Okay, right. Okay, well, that might be a good place to stop. So thanks again, Laura. And all right, can we have the next speaker try sharing their screen?
Hello.
Hi. Okay, I see your screen, but I think it's just a wallpaper right now.
Yes. Let me 1 second.
Sure. Yeah.
Yes.
Oh, looks good. I can see your title slide.
Yep. Let me see if that works. This is the next slide, right?
Yes.
Yeah. Okay. Cool.
Excellent. How is your name pronounced?
Chipen Liu.
Awesome. Okay, let's wait another minute or so till 45 minutes past the hour.
Yep.
Okay, I think we can start now. So our next talk is going to be on tight quantum time-space trade-offs for function inversion. And the talk will begin by Chi-Pen Liu.
Okay, thanks for the introduction. Yeah, today I will be talking about the tight quantum time-space trade-offs for function inversion. This is a joint work with Kai-Ming Chan, Siyao Guo, and Luo Wenqian. Function inversion is the following problem. You are given oracle access to a function f and also some image y, and the goal is to find any pre-image of y. Classically, the problem requires a brute force search, which takes time linear in n, and this is known to be tight. Quantumly, Grover search can be used and achieve a quadratic speedup, and this is also known to be tight. And in this work, we're interested in the following problem. What if we can propel an arbitrary aspect of advice about the function, and then using the advice to do function inversion with fewer queries? This is a real threat to practical cryptography. In practice, breaking a crypto system is usually doing function inversion over some publicly known function f. An attacker would do very heavy pre-computation on a crypto system to get some advice, and later it can use a piece of advice to break the system much faster. It also helps us understand the non-uniform circuit complexity of the function inversion problem. And also, the problem has connections to well-studied problems in data structures and communication complexity. So let's first look at the classical results. The classical algorithm called Hellman's trade-off would achieve the trade-off s squared t less than n squared for functions. In other words, if an s-based advice is allowed, the number of queries to do function inversion with constant probability is roughly n squared over s squared. And the same algorithm achieves the trade-off st less than n for permutations. And for lower bound, Yao and Uru proved a lower bound, which is st greater than n for both functions and permutations. In other words, s and t should at least satisfy st greater than n to achieve a constant probability of inverting. And this is tight for permutations. However, there's a barrier between the upper bound and the lower bound for functions. And later, Corrigan, Gibbs, and Kogan showed that any improvement on the lower bound would result in a new lower bound for circuit complexity. And in this work, we consider quantum query complexity with the following two scenarios, namely classical advice or quantum advice. In other words, we consider an algorithm with either classical or quantum advice and can make quantum superposition query to a function. The only non-quantum algorithm with advice is to use either Hellman's trade-off or use Grover search. That is, given the parameter s and t, one can choose either use Hellman's or Grover's, depends on the parameter. We notice that for this algorithm, Hellman's trade-off is a classical algorithm using only classical advice, and Grover's algorithm does not even use any advice. So in this algorithm, advice does not help speed up the quantum part. Therefore, in this work, we consider the following question. Could advice help speed up Grover search? And this problem was first proposed by Nayebi, Arison, Belov, and Traverson in 2015. They proved the lower bound st squared greater than n for classical advice and permutations. And later in 2019, Han, Sagawa, and Yamakawa, they showed that the same lower bounds hold for classical advice with functions or quantum advice with permutations. And more recently, Chan, Liao, and Chen, they extended the result to the case of quantum advice with permutations and also functions. It only applies to functions whose domain and range are of the same size. But they did not rule out the possibility that a piece of advice would speed up function inversion, because it is still possible that having s bits of advice, a quantum algorithm only needs to make roughly square root of n over s queries. And in this work, we answer the question by improving the lower bound to st plus t squared greater than n for quantum advice and functions. and it rules out the possible speed up above, and we will explain it in the next slides. Now let's draw the trade-offs in the figure. The x-axis is for log of s, and the y-axis is for log of t. Namely, if we have a point in if we have a point 0.5 in x-axis, it means s equals to square root of n. So the Hellman's trade-off gives this line. And the classical lower bound achieves this line. And as mentioned before, there are barriers between this area, the area between these two lines. And for Grover's algorithm, it gives this upper bound, which is this red line. And all the previous results give the quantum lower bound is this blue line, which is st squared less than greater than n. And this orange line is our new lower bound. For s is at most square root of n, it is tied to Grover search. In other words, if the advice is more, then even quantum advice does not help Grover search. And for s is greater than square root of n, the bound is the same as the classical lower bound, which is the best possible lower bound, considering the barrier mentioned before. While improving the lower bound of function inversion, we also provide a generic framework for proving quantum time-space trade-offs and use it to solve the following problem, including Yeltsin box, PRG, and sorting. The first one is Yeltsin box. Let f be a function with binary output, and also assume we're additionally given s bits or sq bits of advice only about the function f. The question is, can we learn f of x by only querying f prime t times? Well, f prime has almost the same functionality on as f on almost all inputs other than x, and it has no information about f of x. And the problem in the classical setting are recently studied in the context of circuit complexity. And we resolved two open questions from Nayebi et al. For Yeltsin box. For classical advice, we show a lower bound which is st greater than n. This is improved from st squared by Nayebi and Han et al. It is tight with respect to a classical algorithm, which shows that the power of quantum query does not help Yeltsin box with only classical advice. And for quantum advice, we show a first non-trivial lower bound, which is s to the fifth times t greater than n. Now let's talk about sorting. Sorting is a common mechanism used in practice for defeating auxiliary input in cryptography. In 2018, Coretti, Dodis, Go, and Steinberg, they show the following theorem. If any crypto application is secure with respect to a random oracle in the random oracle model, then it is also secure against preprocessing with respect to a sorted random oracle. And this is a classical statement. And we extend the statement to quantum preprocessing attack. Our statement says, if any crypto application is secure with respect to a random oracle in the quantum random oracle model, then it is also secure against any quantum preprocessing attack with respect to a sorted random oracle. And as a corollary, we answer the question raised by Han et al. By showing a first lower bound for collision-resistant hash function in the quantum random oracle model. Now let's briefly talk about our technique. Our proof consists of the following steps. First, we reduce lower bounds against advice to multi-instance game lower bounds. The reduction is analogous to direct product problem by Arison, but it is probably stronger. And also the reduction is generic, and the reduction is independent of the applications. By using gentle measurement lemma and also an online version of shadow tomography, we reduce lower bounds against classical advice or quantum advice with decision game to multi-instance lower bound. And second, we give lower bound for multi-instance games while we build and use a technique from Landry's compressed oracle. And based on compressed oracle technique, we prove the following lemma, which we believe will be of independent interest. And now let's consider the following function inversion game. Well, A is an algorithm. It makes Q0 queries to a function. And then it gets the real challenge Y, which is sampled uniformly at random. And then it can make another Q queries to the function. And finally, it needs to output the pre-image. The lemma says the probability of inverting Y is at most Q0 plus Q squared over N. In other words, even the quantum query made before getting the challenge does not help the probability quadratically. It only helps it linearly. We also leave the following open problems. And that's everything I want to talk about today. Thank you.
Thanks for the talk.
Mm-hmm.
We have time for questions. Okay, maybe I'll ask a somewhat speculative question then. So your techniques, so the time-space trade-offs that you consider are where you have so some advice, that's the space part, and then you want to minimize queries after that. That's the time part. People have also studied time-space trade-offs in the sense of you want to minimize the space usage of the algorithm, and the time is still the queries to the black box.
Yes.
In the quantum setting, it seems it's very hard to prove these time-space trade-offs in this scenario where we have, you want to restrict the space of the quantum algorithm uses. And, you know, so for example, yeah, for many problems like element distinctness or something, we'd like to show that if you don't have enough space, then you can't get the quantum bound. Do you have any idea if your techniques would apply in that kind of setting?
I know there's a attempt of using the similar techniques. Basically, you can treat, so for a computation, you divide the computation step into segments, and you assume the time space, the space constraint only happens when you have when you're in the transition of different segments. So you can basically treat the space as an advice, and then you bound. Basically, you just reduce the problem of bounding the space during the computation into a bound of like use advice and to do the computation. Now I know there's some attempt basically using the same techniques, but I think it does not give a tight bound for, let's say, collision finding or element distinctness problem, as far as I know.
Okay. Oh, very interesting. All right. Okay. Let's maybe move on to the next talk. And thanks again for your talk.
Thanks.
All right. So with the next speaker, want to try sharing their screen?
Yeah, I think
Oh, great. Okay. I can see your title slide and I saw your first slide. Okay. Perfect. Okay, let's wait a minute till the hour. How is your last name pronounced, maybe?
Soleimani Far.
Good. All right, I think we've hit the hour. Okay, so our next talk is going to be on sample efficient learning of quantum many-body systems, and the talk will be given by Mehdi Soleimani-Farr.
Right, thanks. So this is joint work with Anurag Anshu, Srinivasan Arunichalam, and Tomataka Kawahara, which is about learning quantum many-body systems. So let me begin with some background from classical learning theory before getting to the quantum setup. So suppose we have n binary random variables arranged on the vertices of a bounded degree graph. A natural choice for a probability distribution over these variables is called the Gibbs distribution, which is defined such that the probability of an assignment is proportional to the exponential of a cost function, which is sum of local terms. The normalization factor you get, which is sum of these exponential factors, is called the partition function, and this whole setup is known as the Ising model or the Boltzmann machine, which is very common in machine learning and statistics. So it is known via the Hammersley-Clifford theorem that the Gibbs distribution has a unique property called the Markov property or conditional independence. So let me explain that. Suppose we divide the vertices into three sets A, B, and C, such that the vertices in set A are disconnected from those in C. Then the Markov property says that conditioned on the variables in set B, those in A are independent of those in C. Or in other words, the mutual information between A and C conditioned on B is 0. So a common setup in learning theory is to use IID samples from the Gibbs distribution to learn these parameters A sub KL that fully determine the Ising model. And there's a rich body of work on this, and people have shown that there are learning algorithms for these models with efficient time and sample complexity. Okay, so far this is all about classical probability distributions. Now, I tell you about a variant or generalization of these models that appear in quantum physics and quantum computing. So now instead of probability distributions, we have quantum states, which are PhD matrices with trace 1. And instead of Gibbs distribution, we have quantum Gibbs states, where the cost function we had before is now replaced by an operator called the local Hamiltonian. So here these EKs are local Hermitian operators that don't necessarily commute with each other, and they form a basis. So you can fix them beforehand, for example, as a tensor product of a constant number of Pauli operators. And once you have them, then you can decompose your Hamiltonian as a linear combination of them. The coefficients you get, mu1 through mu_m, are called the interaction coefficients. So this parameter beta comes from physics. It corresponds to the inverse of the temperature that this quantum system is kept at. And similar to the Ising model, we have the quantum partition function, which is just this normalization factor. So again, we can ask a similar question as we had for classical Gibbs distribution, which is whether there is an algorithm that, given efficient number of samples from quantum Gibbs states, infers the interaction coefficients mu, which fully determine these quantum models. So this is called the quantum Hamiltonian learning problem. And as you see, there are a lot of similarities between what I explained for Ising models and what we have in the quantum setting. But despite these similarities, there are also crucial differences. And most importantly, this Markov property is known to be violated in its exact form in the quantum settings. So this makes carrying over techniques from classical learning theory to address this quantum Hamiltonian learning problem a non-trivial thing to do, because most of those learning algorithms for Ising model and Boltzmann machine, they, in one way or another, use this Markov property. So this is a question that we study in our work, but before stating our result, let me tell you more why we care about this. So from many-body physics perspective, there is this general question that whether we can test or falsify our theories about how interacting quantum systems work in a provable way. And this is despite the fact that we know directly simulating these systems is often computationally intractable. And a similar question arises in quantum computing, where many quantum algorithms involve sampling from quantum Gibbs states. So this appears in quantum annealing, quantum STP solvers, or finite temperature simulators. And again, what we would like to have is a classical algorithm that, given the output of a large-scale quantum computer, determines if the correct Gibbs state has been implemented or not, and like learns what the implemented Gibbs state. And from machine learning perspective, given the success of machine learning techniques in learning high-dimensional data, there is a lot of interest in applying these techniques to problems in quantum physics and quantum computing, where you often deal with state spaces that are exponentially large. So this quantum Hamiltonian learning problem seems to be a natural candidate for rigorously establishing such a connection. There have been various previous works on this problem, but no algorithm with rigorous performance guarantee existed. And this is what our result achieves. We show that order m cubed over epsilon squared IID copies of the Gibbs state is sufficient for learning the interaction coefficients with error epsilon measured in the L2 norm. So m, the number of interactions, is of the order of number of particles. So this is just a polynomial sample complexity. And there's this constant factor depending on beta, the inverse temperature, which blows up as you go to the extreme cases of very high temperatures or very low temperatures, and this is expected. So let me briefly tell you the main ideas in our proof. The first is the concept of sufficient statistics. So it turns out that the knowledge of the exact value of certain local expectations suffices to uniquely determine the Gibbs state and the Hamiltonian, or these interaction coefficients mu. So this is similar to the case that you want to learn a Gaussian distribution, where looking at the sample mean and variance of your input data is sufficient just to determine the whole distribution. We can generalize this to the quantum setting. And one way to do this is using the maximum entropy optimization, where the idea is that among all the quantum states that have some given, that their local expectations are equal to some given values, you choose the one that maximizes the von Neumann entropy. So intuitively, this gives you the least biased choice among all the choices that you have. And then you can show that the output of this is just precisely the Gibbs state whose local expectations are these EKs. And if you look at the dual of this problem, this COMEX program, it gives you the interaction coefficients. So this is all good, but there is a huge problem here. We don't have these local expectations exactly. The best thing we can do is to use the finite number of samples of the Gibbs state provided to measure these operators capital EK and get some empirical averages, which I show by E hat sub k. And then the crucial step left is to show that this procedure is robust to statistical errors that arises by substituting things with empirical versions. So classically, this follows from the Markov property. In the quantum case, we don't have that. So in our work, we lay out a framework that gets around this issue by using other properties of many-body systems, like quantum many-body systems, like the Lieb-Robinson bound or quantum belief propagation. Our main technical contribution is improving the strong convexity of the log of the partition function. So you can refer to the long version of my talk to see why the log partition function is the right quantity to look at and why strong convexity shows up. But it turns out that as long as there is an inverse polynomial lower bound on the minimum eigenvalue of the Hessian of this function, then we can get a polynomial sample complexity. In our case, this lower bound is just order 1 over m, or equivalently 1 over n, the number of particles. And then we can show that Having this, there is only an overhead of order m when going from the errors in the local expectations to the errors in the interaction coefficients, compared to an exponential overhead that you might naively expect from a model that doesn't satisfy Markov property. Okay, I think I'm out of time. So to summarize, we proved an order m cubed over epsilon squared sample complexity upper bound for Hamiltonian learning. In our paper, we also show a root m over epsilon lower bound. So this shows up to polynomial factors our sample complexity is tight. It's an open question to get tighter bounds on sample complexity. And more importantly, our results are only sample efficient because we use these sufficient statistics methods that causes a blow up in time complexity. It is interesting to find an unconditional time efficient algorithm. And these are our results. And I thank you for your attention.
Thank you for the talk, Mehdi. All right, we have some time for questions. All right, if nobody's going to exploit this opportunity to ask questions, I will. I was wondering, this is just a question about the choice of the problem you choose to study. Why do you choose to learn the Hamiltonian L2 norm and not L infinity norm, which I would have thought would be more natural?
Yeah, it would have been nice to have a way to prove this for L infinity norm, but right now we can't do it. The only non-trivial sample complexity we get is for L2 norm, and the reason is that we know how to analyze this L2 norm using this, sufficient statistics and maximum entropy optimization. But to get to the L infinity norm, we need like more refined and like more sophisticated measurements to perform, and they're basically like non-local. Classically, we know how to analyze those. In the quantum settings, the tools that we can work with are all like they rely on the locality of measurements and the problem. So they all break when you try to perform the measurements that people have for L infinity norm. But it's an open question whether we can improve our sample complexity to polylog by switching from L2 to L infinity norm. And this again seems to like be connected to this lack of Markov property in the quantum setting.
I see, yeah, makes sense. Anyone want to sneak in a quick question? No? Okay, in that case, let's thank the speaker again. And let's get the next speaker set up. Thanks, Mehdi.
Well, can you see my slides?
Yep, they look good. And I think yeah, we saw your second slide as well, so it's working perfectly. Okay, let's wait till 15 minutes after the hour. Oh, there's already a question in the audience that you can address. What does MSR stand for?
Microsoft Research.
Okay, maybe let's get started. Our next talk and the final talk of this session is entanglement is necessary for optimal quantum property testing, and the talk will begin by Sitan Chen.
Great, thanks. So I'll be talking about joint work with Sebastian Bubeck and Jerry Lee. So let me begin by saying that when I refer to quantum property testing in this talk, I'll be referring to quantum testing of quantum properties. Okay, so specifically, these are questions of the form: given the ability to measure copies of some unknown mixed state, determine whether that state has a given property P. Okay, so from a mathematical standpoint, this is an appealing kind of question because it's a natural non-commutative generalization of distribution testing. And from a practical standpoint, it's particularly timely to ask whether we can design efficient algorithms for certifying whether the quantum states that we prepare in experimental setups actually satisfy the properties we want them to. Okay, so with that in mind, let me give you a very sort of elementary sort of outline of the classical and the quantum picture for questions of this flavor. Right, so in the classical setup, we're interested in understanding some unknown probability distribution, which lives in the simplex. And typically we like to determine whether this distribution has a particular property or is epsilon far from having this property in some notion of distance. And a common notion of distance here would be TD. Some canonical problems in the space include testing whether P is equal to the uniform distribution over D elements, or perhaps equal to some specified distribution, and this would be called identity testing, etc. Okay. And the model under which we interact with this unknown object is through independent samples. Okay. So in this talk, we'll focus on uniformity testing and its quantum analog. And by now, it's been known for some time that the sample complexity for uniformity testing is within a constant factor of root d over epsilon squared. And so you'll notice a salient feature of results in this testing literature is that the sample complexity that is needed to test these particular properties is substantially less than the number of samples you would need to actually learn the full distribution in total variation. Okay, so what happens in the quantum picture? Here we're interested in not a distribution, but a mixed state. So just a trace one PSD matrix. And the distance to which we want to test properties of this mixed state will be trace distance, for example. And the analogs of these classical testing goals in the left column are things like mixedness testing, state certification, etc. And here mixedness testing is really the question of testing whether your mixed state rho is equal to the maximally mixed state or epsilon far in trace distance from the maximally mixed state. And the query model, rather than sample access, will be in the form of quantum measurements on copies of this mixed state rho. Okay. So before I go into the right sample complexity for the question of mixedness testing, let me elaborate a bit more on this particular query model. Okay. So at a very high level, a POVM specifies some classical distribution, which depends on the POVM and on the mixed state that you're measuring. And so when you say you measure rho with POVM M, you really just mean that you're sampling once from this particular classical distribution. Okay, so say we're given some collection of copies of mixed state rho. Then there are three different ways of designing a testing algorithm based on interaction via quantum measurements. The most basic would be to use the so-called unentangled non-adaptive sequence of measurements. Namely, you pick a collection of POVMs ahead of time, and then measure your individual copies of rho, receive some measurement outcomes I1 through IN, and base your decision on whether rho satisfies the property you're interested in or is far from satisfying based on these measurement outcomes. Okay, so this is sort of like the most simple-minded way of designing a tester. You could be a bit more clever, and instead of picking all of the POVMs ahead of time, you could pick them in an adaptive fashion. Namely, you start with some POVM, you measure and get some outcome I1, and based on that outcome I1, you design your next POVM, etc. Okay. But you could be even more sophisticated, and instead of measuring all of your individual copies of rho one at a time, you can imagine that your n copies of rho are simply a single copy of a mixed state in a much larger tensored space. Okay? And so instead of designing capital N different POVMs, you can imagine just designing one gigantic P of M in this tensor space and measuring with that P of M. Okay, so it's clear that as you go from 1 to 3, the power that the tester has access to increases. Okay, so in particular, entangled measurements can capture unentangled adaptive measurements, which of course can capture unentangled non-adaptive. Okay, so by now, entangled measurements are quite well understood, and algorithms achieving optimal copy complexity for the various testing tasks I mentioned are known. And while these results are mathematically very beautiful, from a practical standpoint, one drawback is that they require pretty large quantum memory overhead. So one could ask, can we get comparable copy complexity guarantees just using unentangled measurements, which are much closer to what one could hope to achieve in practice? And one roadblock in sort of theoretical results on unentangled measurements has been to properly understand the power that adaptivity can afford you. And so the driving question behind this talk is, are unentangled measurements strictly more powerful than unentangled measurements? And in this work, we answer this in the affirmative for the basic question of mixed testing. Okay, so returning to this table from earlier, we can now sort of pin down roughly what the sample complexity for mixed testing is under these 3 different kinds of testing algorithms. So when you have full access to the power of entangled measurements, it was shown by O'Donnell and Wright a few years back that d over epsilon squared copies suffice and are necessary. Our first result is to show that for a non-adaptive unentangled measurements, you need roughly a root d factor more, and this is tight up to constants. And our main result is to show that even with adaptive unentangled measurements, you still need strictly more copies than you would if you had full access to entangled measurements. Okay, so there's this gap between entangled and adaptive measurements. Let me see how I'm doing on time. Okay. All right, so in the time remaining, let me just sketch like at a very high level what the technical, what the techniques are in showing this result. Okay, so the starting point is the particular lower bound instance that we consider. And this is sort of a well-studied object by now. So I call this a quantum Paninsky instance. So you start with any unitary matrix U, and you consider the following mixed state. You start with a diagonal matrix whose entries essentially corresponds to the probabilities in a so-called classical Paninsky instance. And you can think of this as a probability distribution where half of the elements have probability 1 plus epsilon over d, and half of the elements have 1 minus epsilon over d. The particular half d over 2 elements you pick to have the larger of the 2 probabilities doesn't really matter. Okay, so this is some diagonal matrix, and rho sub u is just going to be defined to be the conjugation of this diagonal matrix by the unitary matrix U. Okay, so this is the lower bound instance. And the name of the game is really to show that the following distinguishing problem is hard. On the one hand, consider the distribution over measurement outcomes after you fix some strategy for how to measure using POPMs, if you measure the maximally mixed state. And the alternative is the distribution over outcomes if you had instead measured one of these Paninsky instances, where at the very outset, you sample the U that parametrizes the Paninsky instance uniformly at random from the unitary group. Okay, so in the case where you're using non-adaptive unentangled measurements, you can think of A as really just being some kind of product measure, and B being a mixture of product measures, where the mixture is parametrized by the unitary group. Okay, and in this case, it turns out it's not that hard to adapt classical techniques to give like a fairly clean upper bound on the chi-squared between the alternative hypothesis and the null hypothesis. And the really tricky part comes when you consider adaptive measurements. In this case, you don't have this nice conditional independence structure, and you can't hope for chi-squared to have a particularly nice form. So the main idea in this paper was, instead of bounding the chi-squared divergence, try to bound the KL divergence by using the chain rule. Okay, so this is sort of like the main technical contribution. I encourage you to check the longer talk for details on how to implement this. So let me just conclude in the remaining time with sort of like the main mathematical step in this argument. And it's really to show that the following pairwise correlation quantity is bounded. So given any POVM M and a unitary matrix U, let's define little p to be the distribution over outcomes if you measure just a single copy of the maximally mixed state with M. and let q to the u denote the distribution for measuring a single copy of rho sub u using n, where rho sub u is this quantum Paninsky guy. All right, and sort of the key step is really to understand how the following random variable concentrates. So this is essentially the chi-squared divergence between q to the u and q to the u prime relative to the base measure, which is given by the outcome distribution for measuring the maximally mixed state. Okay, so this is some quantity that kind of tells you like how much a single measurement can let you distinguish between u and u prime for any unitaries u and u prime. And the key lemma is really to show that this random variable, parametrized by the Haar random u and u prime, has fluctuations of order roughly epsilon squared over d to the 3/2. And this is essentially where the non-adaptive lower bound of d to the 3/2 over epsilon squared comes from. Okay, so I'm all out of time, so let me just flash the slide of open questions. I'm happy to take any questions during the Q&A about these. So thanks for listening.
Thanks for the talk, Sitan. All right, we have some time for questions.
Can I ask a question, Robin?
Yeah, go ahead.
So usually the word entanglement is used for states. Do I understand correctly that for you it means that your measurement is not product?
Yes.
I see. Okay.
Yeah. It's just some terminology.
Okay, thanks.
Yeah. Mm-hmm.
Any other questions?
Yeah, Sitan, can you say something about what extra ideas are required to get the adaptive lower bound?
Yeah. So the fluctuations for this pairwise correlation are sort of essential for both getting the non-adaptive and the adaptive. The reason why you see a 3/2, but then the adaptive becomes 4/3 is that there's some like balancing. So when you write out the expression from the chain rule, there's one term that kind of looks like not the pairwise correlation between two distinct u and u primes, but sort of like the chi-square between the base measure and u. So this relative chi-square divergence in this previous slide, you end up needing to bound this for also in the case where u and u prime are the same. And that's really the chi-square divergence between p and qu. And basically there's some balancing that goes on. The fact that basically to handle the tails of this distribution over phi u prime, and yeah, so it's kind of hard to say describe it at a high level, but really like the main technical idea is just to understand the concentration for phi u prime for both of the bounds.
Should it be clear why tails of this thing show up in a different way for the adaptive setting, or for that I need to go understand how the adaptive classical lower bounds work?
Yeah, good. So in the non-adaptive setting, the thing you really need is just, so this is this like Inkster's method, which says it suffices to look at higher moments of phi. Yeah, so then it boils down to just saying like, if phi is sub-Gaussian with the right variance proxy of this like epsilon squared over d to 3/2, then if I look at 1 plus phi raised to the number of copies power, I want to say that the expectation of this is like 1 plus little o of 1. So that's why you need like moments of this guy in the non-adaptive. In the adaptive case, it turns out, yeah, there's like some weird balancing that goes on that we kind of handle in a very like crude way of saying like either this phi is outside of this fluctuation, like this nice fluctuation radius. And in that case, we sort of lose, and yeah, we have to trade off in the exponent. But yeah, I think maybe, yeah.
Thanks.
It's very high level.
Yeah, no worries.
I think I see a question in the chat as far as I understand it. Okay, good. So so the question is like how this relates to the quantum Paninsky theorem in O'Donnell, right? Right. So I think at a high level, like their algorithm, or sorry, their argument is kind of similar, except in the case where you work with like fully entangled measurements, it suffices to like it's necessary and sufficient to upper bound the chi-squared between the Schur-Weil distributions under the maximally mixed versus the like this Pininsky spectrum for the previous slides. So in that sense, it's still doing like chi-square calculations, but in their case, because you can like sort of without loss around, you can like sort of mod out the symmetries from like swapping across copies and rotating within copies. It boils down to some nice thing that doesn't really care about there's sort of like some canonical like optimal entangled measurement that you would work with. So in that sense, it's maybe slightly different. I will say though that there's like an interesting like one of the interesting open questions is, like what is this, like how much entanglement do you need in order to get down to this d over epsilon squared? And their upper bound actually allows you to say, like make the following conjecture, which is that if you have roughly root d over epsilon squared entanglement, it's conceivable that if you have at most that much entanglement, it's conceivable that d to the 3/2 is actually tight. So there's some like connection there that we're still trying to explore. But, yeah.
All right. Yeah. Well, thanks again for the talk, and thanks to all the speakers of this session.